Next talk is going to be anomaly detection of host rules in computer networks. So please give a very enthusiastic applause to Yuri Kasimov.
So good afternoon. My name is Yuri Kasimov, and I'd like to present my work, which was done in collaboration with Stratosphere IPS, which is based at Czech Technical University. This work was originally my thesis, but we continued to develop it further. And Stratosphere IPS, our goal is to protect civil organizations using machine learning. So we provide for them a solution which is open source, and if they cannot afford the expensive methods of protection, they can use ours. Detecting infections and malware attacks is one of the most challenging tasks in network security. There are a lot of amazing systems, such as, for example, Suricata and Snort. But we believe that one of the drawbacks of these methods is that they focus on individual connections and not on the whole user. Also, there is a delay between when some unknown attacks appears and an implementation and deployment of a rule to detect this attack. But also, we are not trying to implement something that would replace these systems, but rather to stack them together and improve the whole security. Anomaly detection, in anomaly detection, we build a model of normal behavior or some model of normality, and then we try to find and detect deviations from this normal model. But there are also drawbacks in this approach, because network traffic is very volatile. It's very complex to model what is normal in the network. So this is why these models, they often suffer from high false positive detections. We propose a method which focuses on the whole user, and we are taking a high-level view on the user, and we believe it will help us to reduce false positive detections. So, as I said, we tried to model a user behavior from high-level point of view. And our method consists of monitoring user computer and collecting traffic during fixed time windows. And with the data collected during this time window, we create a profile which describes what users' actions during this time window. Our hypothesis is that once computer of a user is infected, the behavior of this computer will change in the network, and we want to detect it. So data which we are using are bidirectional flows. I would like to ask, is everyone familiar with bidirectional flows? Please raise your arms who is familiar. Okay, so I will give a small introduction. So flows are defined by this tuple, source IP, source port, destination IP, destination port, and protocol. If we have a device which has enabled creation of the flows, all traffic which goes through this device, all packets are inspected for these parameters, and then they are grouped together into one flow. And bidirectional flow, you have unidirectional flows and bidirectional flows. Bidirectional flow contains information about incoming packets and outgoing packets. And there are two ways how to generate these flows. One is from online from real traffic, and the second is from pickup files using tools such as Argus. And in Argus, we can modify flows a little bit. So Argus will give us additional information, such as bytes which were sent from a user's computer, bytes which were received, and number of packets, flags, and so on. And we monitor a user, we collect flows for an extended period of time, and from features inside this window, we collect flows during a fixed time window, and we extract features from this. And these features are defined what we call a user profile. We have in total 12 features, and they offer us a view on how user behaves, because all actions and decisions that users take during web browsing or work, they transform into packets, and packets are aggregated into flows, and we extract this information. So these features, they offer us a very detailed view how user behaves in the network. We have features which capture number of bytes which user sent to each port, or number of packets sent per each port, or number of flows which were created with destination ports. Then we separate this into established and not established connections. In case of TCP protocol, it's quite easy because Argus gives us flags which were seen during this flow. And if we see packets with sync packet and ACK packet, which went from the user and to the user from the server, we consider it as an established connection. With UDP protocol, it's a little bit more tricky because UDP there is no established connections by definition. But Argus offers us some guess if the connection was established. So if you send packets to some server using UDP and you didn't receive anything back, then Argus puts a flag rec, which means this was not an established connection. And if your user receives something back, then Argus puts a flag con, which means it's an established connection. And then we are using features only for two protocols, UDP and TCP, because they are the majority of protocols seen in the network. And these features are only for IPv4. So each feature is a vector with 65,535 elements. So you have one element of vector per port. And these features, they can be easily visualized with a histogram. I will show these histograms a little bit later, but these vectors are very large, and they most probably will be sparse because computers don't use all the ports, almost never. So we propose some kind of dimensionality reduction technique, which is just increasing bin size of this histogram. So for ports in range from 1 to 1000, we leave bin size 1 because the most important services are in this range, and we want as much granularity in these ports as possible. But for the rest of ports from 1001, we increase bin size to 100. And we believe it doesn't mean we lose a lot of information. So this is an example of, it's the same feature, but So this feature name is client destination port total bytes UDP established, which means they capture how many bytes user sent using UDP protocol, and this was an established connection. On the left, this feature was it's feature of a profile, this profile was captured before we infected the computer. And the feature on the right was captured after we infected this computer. So you can see that infected computer uses much more different UDP ports for UDP connections. And this is what we want to detect. So we used two methods to detect anomalies. One is local outlier factor, and one is one class SVM. Local outlier factor assigns anomaly score to each point based on the density. It compares density of a point to densities of nearest points to it. So I will show you a picture. For example, you see that there are two clusters, and these clusters, they have different density. The cluster in the bottom left is very dense, and the cluster in the bottom right is quite sparse. So, for example, this point with a score 2.5, it wouldn't be an anomaly if you take a look at the whole picture, because the distance between this point and dense, some points in the dense cluster is much less than the distance between a lot of points in the sparse cluster. So local outlier factor compares distance of this point to distances of nearest points, and the difference in these densities is an anomaly score. And I also would like to ask who is familiar with SVM, support vector machines? Okay, so I will also give a brief introduction. SVM is a support vector machine algorithm, which is used for classifying samples into two classes. Here on the picture, you have two classes, green points and blue points. And you can separate them with infinite number of lines. You can have a line like this, and they all will be correct. But you want to make sure that your classifier is robust. And this is what SVM does. It finds such a hyperplane, or in case of two-dimensional features, it finds a line which is such as margin between the closest points to this line is maximum. So even if you will have new points which are somewhere different, it will still be robust in this because it maximizes the distance. But if your points are not linearly separable, then you have to do some tricks to find this line. And one of such tricks is a kernel trick. It basically moves your features into a new dimension, which can be much higher than your original dimension. And then in this higher dimension, you can find a hyperplane which will separate these points. And when you go back to your original two-dimensional space, it will be some complicated curve. And this is this is the basic of one class SVM, which is modification of original SVM algorithm. You have points on the left in the original feature space, and you move them to a new feature space, which where you can find a line which separates these points from the origin. And when you go back, you will have a circle around your points. And if you have and an anomaly is considered a point which is outside of this boundary. And these are two algorithms that we used, and this is a diagram how we trained our models. So we have, for training, we have n profiles of a user, and each profile has 12 features. So first we group each feature together into 12 groups. We do our dimensionality reduction, or it's possible to do any dimensionality reduction. Then we scale our data. And scaling means that we extract the mean from our features and divide it by standard deviation. So our mean will be 0 and variance will be, and we will have unit variance. And on the scale data, we train our anomaly detection models. So at the end, we will have 12 anomaly detection models with 12 pairs of mean and standard variance, standard deviation. And when we want to then we can ask our models if a new profile is anomalous or not. So we do the same scaling on a new profile, on this profile's features. We do scaling, and then each model says, from my point of view, from the point of view of this feature, it's an anomaly, or it's normal. Since we have 12 models, we will have 12 labels. 1 means normal, -1 means anomaly. And then we use majority voting to say if the whole profile is anomalous, because we want to say, to know, this is our goal, to know if it's an anomaly. So to be able to train our models and evaluate them, we needed data sets. And we needed special data sets because for model training, we need only normal data, which are clean but from real users. And the second part is mixed part, which contains traffic from malware and normal traffic. We are not aware that these kind of data sets exist anywhere, so we had to create our own. In total, we created 280 hours of network traffic. We set up a virtual machine in our laboratory, and we created multiple fake identities on Gmail, Facebook, Dropbox, Spotify. And then we were doing what normal user does. We were listening to music, downloading files, uploading files, sending emails. Then we infected this virtual machine, and we continued to do the same thing. So mixed traffic is actually normal user actions and malware actions. But then we thought that maybe we don't need to recreate normal part every time we try new malware. So we recorded new normal part. We took a snapshot on VirtualBox, and we infected our virtual machine. After some time, when we thought we have enough, we went back to our snapshot, so clean machine, and we infected it again with other malware. And this is why second dataset and third dataset, they share normal part, but they have two different mixed parts. So these models, which algorithms that we are using, they have parameters. Local outlier factor has two parameters. One is k, which is number of nearest neighbors, which it will consider when comparing densities. And the second is contamination factor, which is an estimation of how many outliers we will have in our dataset. One class SVM also has two parameters. It has a lot, but we were focusing on these two. One is new, which is upper bound on basically its estimation of anomalies in your dataset. And the second is gamma, which is kernel parameter for the kernel we are using. But you need to somehow, you cannot just throw random numbers and select some parameters and think that it will work. You need to find a correct set of parameters. So in machine learning, we use a technique which is called cross-validation. First, we split our datasets into 3 parts. One is used for training. And the second part is validation, which is used for so you select some set of parameters. You train your models, and then you use validation set to see is my model performing correctly or not. And you select different sets of parameters. You do it over and over again. And at the end, you will select your best model, but you need to make sure that you didn't overfit this validation set. So this is where we use test set. This is the final evaluation of our models. We don't change anything. We just we see what happened on this set, and that's it. Our models are ready. And the next component of training models is labels. We made an assumption that once everything before the infection is not an anomaly, it's normal behavior. And everything after the infection is an anomaly, and we want to detect it. This is, we know that it's a strong assumption, but it allows us to easily label our data without inspecting every packet in our datasets. So with these labels, we made multiple experiments. So the setup was the following. Training profiles, in training set, we have profiles only normal profiles, because for anomaly detection you need only normal data. You cannot have anomalous data for it. And for validation and test sets, we grouped together normal profiles, because we want to know if our model does not mark them as anomalies, which means it doesn't have a lot of false positives. And in these sets, we had profiles with labels anomaly. And this validation set and test set, they didn't have any intersection. The profiles there were completely different. For evaluation, we trained our models with train set, and then we computed metrics on validation set. We cared the most about true positive rate and false positive rate. So false positive rate basically says how many mistakes, how many normal profiles your model labeled as anomaly. And this was what we wanted to minimize. And these are the results that we got. So in the first experiment, we used one class SVM algorithm, and we trained it on the first data set. The validation was done with the profiles after an infection with Emotet malware, and we also tested with Emotet, because this was one dataset, and we didn't want to mix datasets with each other. And our true positive rate was 0.44, and false positive rate was 0. So the positive rate is quite low, but if we use 5-minute time windows, and we basically detect every second profile which is anomalous as an anomaly, we detect each second profile on average, which means you would be able to detect an infection after 10 minutes. again, on average. And in the second experiment, we also used one class SVM trained with normal part from the second dataset, and validation was done with DarkVNC malware. In this case, we had two mixed parts which were done with the same, like, connected to this normal part. So we validated with DarkVNC, and then we validated with Simda malware. And Simda malware gave us 0.2, and with DarkVNC we got only 3% of detection, because DarkVNC, it's a remote control which is quite silent and it doesn't generate a lot of new traffic. But false positive rate was also zero in both cases. And Simda wasn't used in any validation, so this was completely new attack which we kind of also successfully detected. And the local outlier factor in the third and fourth experiment, we got similar results, a little bit lower. They are quite similar to the one class SVM. So on average, we were able to detect each second, each third profile, and it means that once your computer is infected, some alarm will we could raise an alarm during the first 15 minutes. And we successfully detected 2 types out of 3 types of malware with one class SVM. And we achieved our goal, which was to reduce false positives, but it's on our dataset. It doesn't mean our algorithm is perfect in this sense. We need to do much more evaluation and to see if it's actually true. Then we continued to make more experiments, and we wanted to test on IoT devices such as cameras and Raspberry Pis. So we trained with 1 day of traffic from a camera using 5-minute time windows, and then we started to classify profiles in the following 7 days. And we didn't find any anomalies there, which doesn't mean our model works, but it was something that we expected. But after some longer period of time, we started to get anomalies in the camera traffic, mainly in UDP protocol. This is still work in progress. This discovery is quite new for us, so we didn't have time to actually go into pickup files and analyze packets if what's going on. But we think that the behavior of a camera somehow changed, and it caused these anomalies these anomalies later. And with Raspberry Pi, we did a little bit different experiment. We also trained on traffic from clean Raspberry Pi, and then we infected this Raspberry Pi with Chiton, which is a Mirai variant. And after the infection, we got approximately 40% of profiles were marked as anomalous. And again, we didn't have any false positives. We didn't classify any profile which was created before the infection as anomalous. In conclusion, we need to make more experiments with different malware samples, because creating datasets is difficult, and it took us a month or even more to create these datasets. So we need more datasets with more malwares to evaluate better and deeper our algorithms. Also, we want to use our approach to detect changes in IoT devices, such as cameras. And since we can see anomalies per feature, we can say that, for example, camera has more unestablished UDP connections, which could be a quite interesting topic for us. And anomaly is an anomaly, so it doesn't mean it's an attack. It can be network problem, misconfiguration, anything. This is why it's so difficult to detect. Thank you for your attention, and if you want to contact us or me personally, you can use Twitter or my email here. That's it.
Thank you very much, Yuri. We already have a question, which is awesome. Thank you.
Yeah, first just more like a command. You should use ports to up to 1024 because they are privileged in Linux, for example, and maybe then use 128 for the bucket size. Just a comment. When you are training, when you would do that in a real company or something, how would you ensure that your training set is not polluted?
Yes.
That's one of the questions I have. And
Let's answer that one and then.
yeah.
Okay. So thank you for your question. So we know that if a network, your computer is already infected, it will be normal from the point of view, from our point of view. This is, as far as I know, it's an open research theme in the community. It's quite difficult to do anything. So this is what we want to address in our further work. Now we don't have a solution, just use available tools such as antiviruses, Nord, Suricata to at least make sure that it's somehow clean.
Okay, I expected that this is a hard problem, that's why I asked. The second thing is I guess you didn't try that, but what would be really interesting if you go from your normal training set to something that you know is also normal in some other setup, and check and look how much false positives you have there. So to speak, some sort of out-of-sample performance, not including all your data you have, but it's a separate data set. So collaboration with other research teams or something like that would be very interesting insofar as you get an answer to the question, how general is our training data?
Yes. If I understand it correctly, you're asking if it can take our models and apply it to other computers, or
if you use other training data
yes.
from, say, another
Yes.
research group and verify your data, your model against their data,
Yes.
and look how much mismatch you get.
Of
I
course,
expect
yes.
certain types of
Yes.
errors, but it would be very interesting to verify how good your model of normal user behavior
Yes.
would be.
Thank you.
Further questions? We still have a little bit of time left. Anyone? Anyone? Bueller? No.
Thanks. So I had a question on the majority voting.
Yes.
So why did you go with that approach instead of maybe using something like a neural network that gets each model as an input, or some other approach, for example?
Yes. Thank you. This is a great question because we discussed it a lot. We know that majority voting is super basic, which doesn't take into account a lot. It basically means each feature has the same weight. But for training neural nets, you need data, a lot of data, usually. And this is what we were missing. These data sets that we created, we consider them quite small, and we don't think it would be possible to train a neural net model on with this amount of data. But we want to improve our majority voting for sure.
Further questions? If not, we will restore normality as soon as we know what normal is. And I would say we give another very warm round of applause for Yuri. Thank you very much for your talk.